Okay, so I've told you you can measure g by doing the slope of an acceleration versus ramp slope graph, right? And I've mentioned today that if you do it with a ball, that doesn't work. But it turns out if you do it with a car, it does. Okay? And it works quite well, even though there's friction. The friction doesn't really affect the slope for reasons that we'll delve into after we get the basic idea. Okay? Well, the reason you have this is simply that, okay, well, here's your acceleration, mg sine theta, and I forgot the I on there, but there it is, okay? Where I is the direction along the ramp. So, and you know what? This is not your acceleration, this is your F net. I wrote down the wrong symbol there. I really do kind of know what I'm doing. Acceleration's F naught over m, right? So when I started to use this, I said, wait a minute, what's that m doing there? Well, it's g sine theta times I, right? Okay? Understand that I wrote A here and then tried to use it and realized that's not A, that's F net, because of course it was F net up here, and A was gx times I, which I could have done just written right here. Okay, so anyhow, the magnitude of A then is g sine theta. Okay? And as I hope you understand, sine of theta is approximately equal to theta if theta is a small angle. I'll draw a quick picture, but you did this when you proved the derivative of the sine back early in your first semester calculus. Okay? And it's an important approximation. Now theta has to be small, okay? So when we measure this, we use small angles. We don't use a big old steep ramp, we use small ramp, partly because on ramps with small slopes, you don't have something that happens very quickly and is challenging to time, right? If we use a couple of small slopes where things take on the order of a couple of seconds to happen, we can time them with pretty good percent accuracy, okay? So for that reason, and the fact that what I'm about to do doesn't work if theta isn't small, we do this experiment with small slopes, which is what you had. Those slopes were small enough to get us a good result. Okay? So acceleration is approximately equal to g times theta, isn't it? Okay? Also, slope is a tangent of theta, right? Rise divided by run. If your trigonometry isn't up to that, and if you haven't encountered that a lot of times, you really need to lock it in. Slope is tangent of theta, which is also approximately equal to theta. Since a tangent is the sine over the cosine, and the cosine of a small angle is essentially 1, you get the sine, which is theta. Now you can prove this directly. So acceleration is g times the slope, right? So on a graph of acceleration versus slope, slope of the graph is approximately g. Now, by slope here, I don't mean slope of the graph. Okay? So let's be clear, we'll call this slope of the ramp. So I'll put the word ramp in here. We're graphing the acceleration versus the slope of the ramp. Since acceleration is approximately equal to g times the slope of the ramp, the slope of this graph has to be g.